Hello everyone, welcome to this special virtual eCAADe session. I'm Nam Bai, PhD researcher at TU Delft, Faculty of Architecture and Built Environment. In this video, I'm going to present the result of a research using serious game to search for consensus of multiple stakeholders in an urban redevelopment process. We formulate the complex negotiation progress as an abstract and discrete decision-making problem mathematically involving multiple actors. Simulate the progress with different democratic levels using real-world participants through role-playing games, and analyze the gaming process computationally with game theory and graph theory. The authors of this paper are Nam Bai, Shivin Azadi, Pirut Nourian, and Anna Preda-Rodgers from the Department of Architecture, Engineering and Technology, TU Delft. The simulation was undertaken during an international workshop on democratization hosted at TU Delft within the ITN Harryland program. The prisoner's dilemma appears mainly because the participants lack the chance of negotiation and vision on the possibility of the existence of a win-win solution. Similar dilemmas exist in other multi-actor decision-making problems, for example in an urban development planning process. Different stakeholders are involved and they typically have different kinds of stakes and concerns. Thus, conflicts of interest can naturally arise, making the search for consensus like solving a puzzle for which there's not even a guiding picture. To guide all the stakeholders participating in finding a consensual and yet reasonable solution, a simulation game can be helpful for regulating the negotiation process. In this research, we apply a fictitious yet realistic scenario of heritage-intensive campus redevelopment project in TU Delft. For each of the possible sites being discussed, several choices are given. For example, maintain, conserve, adaptive reuse, densification, etc. A set of stakeholders or agents will participate in the game. All the agents are directly or indirectly related to the campus redevelopment issue, thus having their own preferences and judgment criteria. The game proceeds following the diagram shown here. The agents will need to propose new actions or choices to each site or objects. After the negotiation with the group, they will vote for the current configuration of choices each round. The agents are asked to strictly obey the preference and judgment criteria formally assigned for them. The game lasts for 4 rounds, during which the agents will have to primarily seek for consensus and furthermore seek for maximum benefit of the whole group. Parallel to the real-world simulation, all the preference type function of the agents, the utility function of the individual and the group, as well as the voting function, are all formulated mathematically. For the 3 groups participating in the simulation, we set up 3 different levels of democracy as game settings. Though for all the groups, the agents have the same judgment to the choices, and the choices have the same potential social benefits. The power structure, namely the voting weights, are different across the 3 groups. The votes of some agents do not count, though they are invited in the discussion. As it is quite obvious for us what for a decision will be consensual from this diagram, the information is unknown to the agents, and they have to negotiate and reveal gradually the whole picture. The decisions made by each group during the simulation is shown here. All the possible combinations of choices and objects are represented around a circle. Each decision is visualized by a polygon, connecting the object choice pairs. The group started with the same initial decision and changed differently over the rounds. As each group only voted for 5 different decisions including the initial one, the total number of possible decisions reached more than 15,000, which is demonstrated here as a polar coordinate decision graph. Each decision is shown as a colored node on the graph. The closer the decision gets to the center of the plot, the higher the benefit is for the society. Green nodes are consensual decisions, the red nodes are non-consensual decisions. The progression of decision-making over the rounds is also highlighted. Interestingly, Group 2 and 4 both managed to reach consensus in the end, though Group 2 has far less consensual nodes compared to Group 4 due to a higher level of democracy and broader involvement of agents. The dynamic of the social benefit to the group, the traverse distance, and the leap difference function, which is the relative difference of the performance of the group in each round, are also plotted and shown here. As is visible in the plot, Group 1 and 2 have explored more of the decision graph compared to Group 4. The social benefit of all the groups have started from the maximum value, and only Group 2 has finished the game with the same social benefit. And we know that in Group 4, the players whose votes were dumped have campaigned for a fight in Round 2, and they have influenced the decision of the next round. We can measure the effect of such a specific dynamic by looking at the negative leap difference function of that particular movement. The game presented in this paper is a one-off example of an urban planning problem. Even though most such planning problems are unique in their natures, we have sought to ensure that our proposed framework is as general as possible so that it can be applied to other participatory planning problems. Naturally, we have chosen generality over completeness. The framework is outlined in the paper in fully mathematical details. The computational experiments were conducted after the game has already been played, only to analyze the results and explore the potential of our mathematical framework. Having conducted this experiment, we can conclude and argue that such decision-making processes are at least as complex as our framework, and that the sophistication in the regulatory process should be adequately high to be of any use. The main use of such regulatory framework is to ensure equity, which is fairness and inclusivity, in such decision-making processes. Further computational simulations are needed to ascertain whether computational game players are less or more effective than human teams. However, qualitatively and pragmatically, we can conclude that not only human teams can be more effective in playing such games, but also that involving human players so early as this is a democratic must to ensure all relevant voices are heard. In other words, this is not only a computational science question, but rather a political question or social science question. Thank you for listening.